This brings us to the rise of ozone. The rise of atmospheric oxygen would have led to an increase in stratospheric ozone. Ozone ultimately is a product of reaction in the atmosphere. Ozone is critical for advanced life because it protects it from ultraviolet radiation. There have been considerable variations in atmospheric oxygen over the last 2 billion years. Now, when we look at a comparison between energy flux and wavelength of incoming radiation from the sun, you can see here's the visible range of radiation from 400 to 700 nanometers. To the left, we have ultraviolet radiation, and you'll notice that there's a band of ultraviolet radiation that isn't particularly harmful. Once we get into the harmful band of ultraviolet radiation, fortunately, we have an increase in ozone. O3 is a triatomic molecule of oxygen. It absorbs incoming harmful UV radiation, the shorter wavelength UV radiation. So it's fortunate for us that this ozone layer exists and that it persists. The initial increase in atmospheric oxygen and ozone occurred over 2 billion years ago. This does not require that oxygen concentrations jumped to the present level of about 21%. We believe that oxygen concentrations remained far below the present level until just before the beginning of the Cambrian period, and that turns out to be critical for the beginning of the Cambrian period. We see minerals such as detrital uraninite and pyrite that are weathered from a source rock. They're transported and deposited in anoxic environments. If they were deposited or transported in the presence of oxygen, they would have reacted with that oxygen. The pyrite would have rusted and the uraninite would have been oxidized to uranium oxide. When we see things like red beds, these are sandstones that are often bright red, we know these are iron-rich, and they're very strong evidence for oxygen-rich environments at the time of deposition. Here's another. This is from Custer State Park. It is probably Triassic, I'm guessing Spearfish Formation, but I didn't get out and look at it. A couple more shots. These are the rocks that make Zion National Park famous in southern Utah, Navajo sandstone, and another shot of Navajo sandstone near Antelope Canyon in northern Arizona. Moving to Canada, a little bit west of us here, we come to what's known as the Ediacaran fauna. These are multicellular organisms. They're recognizable. They're not what you consider gigantic. They are visible to the naked eye, and it turns out they're pretty weird. These strange animals appeared during the Vendian about 560 million years ago. What's the problem here? Why did it take multicellular organisms so long to evolve if the basic building block was there 2.7 billion years ago in the form of a eukaryote? One idea is that oxygen levels were too low to support them. The Ediacaran fauna have flat bodies, and you'll see they have some complex body forms that increase their surface area to volume ratio and therefore could increase their intake of oxygen. The prime location, the original location, is located British Columbia, right beneath this dot. Just recently, a couple more locations have been found in the Canadian Rockies. And to put us in a time context here, this is the Cambrian, so the explosion of life took place during this period of time. This period of time is known as the Ediacaran. So about 635 million years ago to about 543 million years ago is the Ediacaran. Now, some of the body plans that we find in the Ediacaran fauna include Dickinsonia here, a flat organism with lots of structure to further increase the surface area of this creature. Another here with a segmented body. These could potentially be gills or gill-like features, and a strange snorkel-like grabbing, biting feeding tube here makes this one of the more distinctive Ediacaran fauna. This is another one that strikes terror in the hearts of people, unless you saw how big they really are, which is pretty small. However, they were likely the terror of the seas 560 million years ago. Again, strange body forms we don't see any longer. They didn't make it through the extinction events. This is hallucinogenia and Mirella splendens. When we talk about variability in oxygen, our best record of variability in atmospheric oxygen comes from the Phanerozoic. A little closer to the modern world, things are better preserved, and there's more of those things that are better preserved. The Phanerozoic eon, during which multicellular life thrived, began 542 million years ago with the Cambrian explosion. And this is a time that animals began to make hard parts. This is one of the reasons we see this explosion of life during the Cambrian. Animals started making parts that would be easily preserved. The Ediacaran fauna were soft-bodied. They require very specific, relatively rare depositional events for them to be preserved. So it's thought that this explosion of life is related to a burst in oxygen. At this time, it's thought that perhaps oxygen levels went to 20%, like we see today. We don't have good records of oxygen levels, but we do have good records of carbon storage. And as we've been talking about earlier in the course, a record of carbon storage can provide us with a record of oxygen. The more carbon stored, the less CO2 in the atmosphere as well. During photosynthesis, plants consume carbon dioxide with a preference for carbon-12. Organic carbon that's buried has a higher proportion of carbon-12 than the atmosphere. This means that the atmosphere becomes enriched in carbon-13 because the carbon-12 is taken out of the system and buried. During the mid-Carboniferous period, carbonate sediment delta-13C values were about 5 per mil higher than today, indicating that a large amount of organic carbon was buried, hence the name Carboniferous period. The peak of this period of coal deposition was during the Pennsylvanian epoch, 325 to 286 million years ago, forming the basis for coal mining in western Pennsylvania and West Virginia. That's the expensive anthracite coal, the dark, dense, shiny stuff. Here we have a record of Phanerozoic variability in carbon isotope values. Researchers have suggested that the giant insects of the Carboniferous and the dinosaurs of the Mesozoic may have been breathing air much richer in oxygen than what we have today. These insects have respiratory systems that consist of spiracles, tracheae, and tracheolae that limit their maximum size. That's why insects are the size they are today. They're limited by the ability to get oxygen into their bodies. And another idea for the size of the insects was that biological competition wasn't as intense as today. I don't know about that, but 70-centimeter dragonflies would probably make an easy target for birds today. Modern controls in atmospheric oxygen, we don't really understand them. We don't know what constrains the movement of oxygen in and out of reservoirs. Now, if atmospheric oxygen becomes too high, as was seen here, this is Apollo 1, the astronauts Grissom, White, and Chaffee were killed when a spark ignited under one of the seats. Because they were using pure oxygen inside the space capsule, it burned up in a flash fire. They had essentially no time to react other than say there was a fire. Now, this is something that could happen in the case of forest fires. With an oxygen concentration of 35% or more, a fire could ignite and burn most of the global flora. This might have happened 65 million years ago after the impact. There's some vague evidence that it happened. I don't know if I buy it, but it's an idea out there. Forest fires can also be used as a lower limit of atmospheric oxygen. If the oxygen concentration goes below 13%, forest fires either shouldn't ignite or they shouldn't propagate. Certainly not the way they do at 20% oxygen that we see today. So you can see here this range. Below 13% or so, we're not going to be subject to large environmental fire disasters. Above 35%, we can't do anything about them. We wouldn't be able to stop it. Now, when we turn to oxygen in the netherworld, the deep ocean, most organic matter buried today is deposited in marine sediment rather than in terrestrial sediment. This is likely to be the case for the last several hundred million years, except for the Carboniferous period, known as the Carboniferous period because there was so much carbon deposited. Deep ocean water contains a relatively high concentration of dissolved oxygen because it originates at high latitudes where temperatures are low and oxygen solubility is high. That's a strange thing about oxygen, is its solubility increases when temperatures go down. Now, when we look at the oxygen concentration with depth, we would call this a Caltech plot, sort of something versus nothing. We can see that near the surface, we have relatively high oxygen, and that's due to photosynthesis and some exchange with the atmosphere. As we sink, as the organic matter that's generated in this photic zone sinks, it decays. And it decays by using up oxygen, seen here. So the sugars are going to be respired by bacteria in this decay. It's generating CO2 and water as waste products. Once we go below the oxygen minimum zone, where decay is no longer as rapid, so decay rates slow, therefore the oxygen consumption slows, our oxygen is replenished in these deep waters from the high latitude supply. So in the shallow waters, oxygen is exchanged with the atmosphere and produced by photosynthesis. In the deeper water, the oxygen is supplied by bottom water formation. One theory is that lower oxygen in the atmosphere would result in lower deep ocean oxygen, which would in turn permit increased burial of organic carbon. This would ultimately stabilize the amount of oxygen in the atmosphere. However, we don't have any data to support this idea. It's probably not going to go forward.